parts of the world. We reached the third day of ShaktiCon successfully with really amazing trainings and speakers and panelists. Since 2 days. Today we have Allison. Allison is a researcher and a senior software engineer with an interest in cybersecurity. She worked as a software engineer at Signal Sciences, Mozilla, FactSet, and Amazon, and did her bachelor's from CMU. Fuzzing and vulnerability research are especially interesting to her. She mentors disadvantaged high school students in programming and robotics, and adult underrepresented minorities transitioning into or expanding their career into technology through Portland Women in Tech Initiative. She is also a core member of Blackberry. Hearty welcome to you, Allison, and over to you. The virtual stage is yours.
Awesome. All right. Good morning, everybody, or good evening. Since it is rather late for me and rather early for many of you, I'll try to keep this a little bit whimsical and lighthearted. Let's see. No. Yes. Okay. I can click. All right. So another thing to mention is there's more than one Allison Naaktgeboren. So if you try to find me on the internet with questions or you want some help, please make sure you get the right one. When we get to the lab, I'll have my email and my Discord handle up to remind you. As Bria said, I am a grad student, but I am an old software developer. I worked a number of places. Since this is hosted by a CTF team, I'd also like to point out that I am a member of 3. I'm the president and co-founder of the Portland State team. I'm the captain and co-founder of QQQ, which is an all-women's team here. And I am a somewhat incompetent player on Samurai. Spoken at a couple of places, and I'm involved in a lot of communities. I would also note that the security lab at Portland State, with the exception of our advisor, is currently all women. But that was a nice touch. So what are we going to do today? Again, this is rather early. This goal is to equip you to understand fuzzing. Based on what folks are about to say in the Discord, I gather most of you are relatively new to computer science and or security. So this is not going to be super in-depth, but it's supposed to be a roadmap to help guide you. We're going to talk about what fuzzing is, understand the fuzzer differences, understand some fuzzer limitations, figure out who's interested in fuzzing, why, and what fuzzers might suit which group, talk about a specific fuzzer, AFL, and some of the pitfalls I've seen new students. And then we're gonna get our hands dirty and play with Heartbleed. Everybody with me so far? Cool. We'll take questions at the end. So I've been regularly stopped, literally, metaphorically, and figuratively, in hallways with this question. What's this new fuzzing thing I keep hearing about? It's an exciting research area. I hear it's got lots of papers and funding. Or I hear I can use fuzzy and make a lot of money on the internet easily. That sounds super cool. Wu says, you're the department expert on fuzzing. How do I make money? And fuzzing is a little bit more complicated than I think some people let on. So let's start with what fuzzing is. It is a dynamic stochastic software testing technique. By that, I mean dynamic, we're gonna run the code. So if you have something you are afraid to run or run repeatedly, fuzzing may be a bad fit for you. And stochastic is a fancy word for we rely on probability. We're gonna use a lot of probability here because we're gonna flirt with the halting problem without going too far over. And ultimately, we're testing software. Its goal is to thoroughly explore the input space of a target program, also called a victim program, looking for input or seeds that cause interesting behavior. You should know that interesting is not universally defined. We don't all agree on what constitutes interesting. It does require the ability to reach any input in the input space. On a computer and in computer science, this is pretty easy. Everything's ultimately a string of bits. But if you were to try to apply fuzzing to areas outside of a computer, you might run into some troubles if you can't actually do this. You also note, since Anger has had a couple of presentations, that some people consider symbolic execution to be a subset of fuzzing, others don't, depends on who you ask. And it's not actually new. Fuzzing was first published by Dr. Bart Miller and his students in December of 1990. In a magazine article, actually, it wasn't even a full paper. So it's not actually new, it's over 30 years old. And then if I've thrown a lot of vocabulary at you in the next couple slides, I do have a cheat sheet here. Let me know if it's helpful. If it's not helpful, if you think it's missing something. I personally struggle when I see talks in new area with some of the vocabulary and jargon. So this is my attempt to make this easier for you. So fuzzing at the 50,000, 100,000 foot level looks like this. All fuzzers begin with this sort of series of steps. Some of them can be incredibly complicated, sophisticated works of art, but at its heart, all fuzzers follow this format. There's some sort of setup. Either it's done for you or done by some piece of the fuzzer or the software system. We might prep the target. We might select some inputs to start with. We might tune some parameters. We're going to kick the fuzzing job off. We're basically running a giant while loop, checking if an exit condition has been met. If it hasn't, we're going to choose some series of inputs to test. And for each of those inputs, we're going to feed it to the target program in a little experimental box and see what it does. If it does something we think is interesting, we're probably going to store that result. We might update some bookkeeping. We might do some deep thinking about what to do next, and we'll move on to the next input. And we'll do that until something tells us to stop. All fuzzers have this characteristic. Basically, we're going to run the program with the input and see what it does. But this gets a little, it's a very broad view. So let's talk about how fuzzers are different and how they go about solving that problem. A couple questions. The first one I always ask a new fuzzer is, how do you define interesting? Where do you get your seeds or your inputs? What's the exit condition? How much do we know about the target? How much do we need to know is another way to think about that. Does it have a focus or specialty? And does it have some sort of secret sauce that makes it super awesome? So the one we're gonna start with is, how do you define interesting? To me, one of the things that's most interesting about fuzzers, pardon the overuse of the word, is how they figure out if a target program has done something they should care about. Now, these are the four big ones, but there are many more, and they can be combined. These are not mutually exclusive. Right now, code coverage-based fuzzers are very big and the most common, so I'm gonna start there. In a code coverage-based fuzzer, interesting is defined as an increase in the code coverage graph. It may not actually be a graph, but I'm going to use that abstraction to sort of get the idea into your head, and because it makes a nice comparison and contrast with directed fuzzing. People who are experienced in fuzzing will know that I am deliberately eliding some details. If you're new, don't worry about it. So in our contrived example, artistically rendered for you here, we have seed 1, which finds these 4 nodes. Okay. Works for me. Seed 2 finds the same 4 nodes. Well, that's not very interesting. We didn't learn anything we didn't already know. Seed 2 is not interesting, but seed 1's okay. And then we do seed 3, which finds us a new area in the binary. Oh, that's very interesting. Seed 3 is officially interesting. So anything that causes new areas to be hit is considered interesting in code coverage-based fuzzers. In a directed fuzzer, we don't care about coverage. We care about getting to a specific point. We have a target. That, get me that. I want to get to that thing. So in a directed fuzzer, we are looking for things to get us to a point, and anything that gets us closer than we've been before is interesting. So our first seed, we find the same 4 tuple. It's a start. You know, it's not very close to the green dot. Our second seed, we get closer. We're still 1 off. And in our third seed, we get to the target. The third seed is the most interesting of all because it has gotten us where we want to go. Seed 2 is the second most interesting because it got us closer than previous seed. And seed 1 is just not really interesting at all in the grand scheme of things. Another thing you'll frequently see is taint analysis, also called taint checking or taint tracking. I don't know why we can't quite agree on a terminology, so I'll give you all 3. And that does something a little bit more sophisticated, particularly for security applications. So we want to get from some sort of source address, here indicated by red. And security, we're usually interested in sources that are user controlled. So some sort of user controlled input or memory. And we want to get to the green, which is something like a UUID or a password or some sort of sensitive data we want to get to. And we're interested in paths and inputs that cause us to get from the red dot to the green dot. This represents our ability to use user controlled input to get to places we're not supposed to. And you can do that by attempting to navigate sort of the code coverage graph, looking for paths that get you from one to the other. And then last but not least, crashes are eternally interesting. Anything that sets the target on fire is generally considered a very interesting input because we assume that targets are never supposed to crash. So when they do, they've automatically done something interesting. Next question is an exit condition. This one's a little bit easier to wrap your head around. When do we stop fuzzing? Well, above and beyond is the most common one, is scheduled duration or user-initiated exit. We basically run the fuzzer until something outside tells us to stop, whether a timer or a user's control C. Some fuzzers will run until they run out of inputs. And some fuzzers will take it one and done. As soon as they find one interesting seed, they exit. We'll talk about who might want to do this and why a little bit later, but it does exist that some fuzzers exit as soon as they find one interesting input. So next question, which is of course very relevant to my research, is where do you get your inputs? You can also think of this as what happens to your inputs at each iteration of the fuzzing algorithm. Your fuzzing algorithm may run millions or hundreds of millions of times before you're done. So what happens can be very important. This is an excellent area for research and innovation. But the three big ones right now are mutational, generational, and the classic or naive. Mutational is currently one of the biggest ones, and it works by taking seeds that did well prior and tweaking them a little and seeing if you can get them to do even better. So in our case, we started with a seed with a picture of a cat. That did okay. So we're gonna twiddle some bits in the cat and see if we can make it do better. If that does really well, then in the third iteration, we're gonna add lots of whiskers and see if that does extremely well, or maybe it'll do terribly, we don't know. But we're gonna try it since adding whiskers worked before. Notice that you are changing something from one iteration to the next. And so you care about what happened in the prior iteration. These are sort of chains, and they're sort of dependent on previous behavior, and that can inform the choice of behavior of a mutational fuzzer. Contrast that with a generational fuzzer. A generational fuzzer doesn't start so much with inputs, although some of them do, but with an algorithm or an idea. You can think of it as assembling its seeds rather than mutating pre-existing ones. In my contrived example here, we know we need 2 ears, 2 eyes, and a nose. And I'm gonna pick from each set and assemble it into a thing and try it. A generational fuzzer doesn't necessarily care about what happened in the prior iterations. It can be a little bit more parallelizable because they are much more independent operations. If you see something to describe itself as a grammar-based fuzzer or a protocol-based fuzzer, there's a good chance that most of the seeds are generated, and then we might mutate specific bits. Algorithms can get mix and match. Sometimes they'll generate, sometimes they'll mutate, sometimes they'll just pull from dev rand. All this can be part of it, but when we generally describe it in algorithm, we tend to pick one or the other big categories. And then last but not least is the classic, the original fuzzer, which basically uses some source of randomness and takes whatever randomness you find and shoves it in there. It doesn't really worry about prior or future seeds. It just tries randomness. You might say, I need a picture of the cat, and you'll get a Jackson Pollock painting. You might get a picture of a fish. It's totally random. Random fuzzers do get a little bit of a bad rap, but in practice, they're surprisingly effective. And then the fourth question is, what do we need to know about the target? Start from the top, which is white box. In a white box, you usually have source. You essentially have everything. And if you have the source, you can compile or JIT your target to get a black box or gray box binary if you so desire. But white box fuzzers usually means they're interested in working with the most complete information available. A black box fuzzer is able to handle a binary. You have no information beyond the compiled and presumably optimized binary. Nobody should be shipping unoptimized binaries in production. So if you see a binary, it's probably optimized. And if you know anything about C++ or Java, we lose a lot of information on the way down to compilation about the state of the original program on the source. Some fuzzers care a lot about having that, others don't. And in the middle, and the most common form we're seeing right now is something called gray box, which will be spelled whichever way you prefer. I'm not picky about how you spell gray. And that is a binary that's been compiled with special instrumentation. So we'll have things like address sanitization, code points, barriers, memory checks built in. One of the catches with gray box is you usually need the source to compile in all that special instrumentation because you don't get it by default. Now, there has been some interesting research work about how to take a binary and retroactively shove all that instrumentation into it, but I haven't seen a lot of it used in production. But it's an interesting area of research. And then, does it have a specialty? Some fuzzers are built for specific tasks. BooFuzz is meant to fuzz network protocols. Syscaller is built for Linux. AFL Win is built for, you guessed it, Windows. I've seen a good dozen fuzzers come out aimed at IoT, such as routers or other small appliances. I've even seen a small fuzzer written for the network in your car. And it too is surprisingly effective despite being a naive fuzzer. So if a fuzzer is built for a specific application and you're interested in that application, it might be a good fit. And then the most interesting question is always, what's the secret sauce of this fuzzer? Does it have some sort of advance in the state of the art, some sort of really cool algorithm or optimization? Does it target rare branches? Does it have a power optimization? Does it have a scheduling optimization? Does it do something interesting with power management? Do we combine it with symbolic execution? Does it have special emulation properties like being mixed with QEMU or Unicorn? Does it have ML, AI, deep neural network magic in it? All these fuzzers usually have something special about them. Whether or not it's useful for your task is sort of an open question, but it's good to ask what a fuzzer thinks is special. So if you want to read how you define interesting, what the exit condition is, how you get your seeds or what happens to them, how much do we need to know about the target, does it have a focus or specialty, and does it have a super secret sauce? If you can answer those questions about a fuzzer, you've got a pretty good grasp about its strengths and its weaknesses. But please remember that fuzzing is not magic. Now I've run you through some of the major algorithmic blocks rather quickly that we have, and that should probably be suggesting to your brain some sort of things for which fuzzing may not be good, or some of the limits. So the first one that I think a lot of people run into is not the theoretical nice one, but the practical one. It's extremely hard on your hardware. It's CPU intensive, it's often RAM intensive, it consumes a lot of power and potentially electricity. All that stuff costs money. Now, I know a number of people who are offensive researchers, and they basically run the fuzzer in the background on spare hardware when they're not using it. So they don't really care about the power consumption. But if you are thinking about using this in a professional setting as part of production, then that power cost can add up. Likewise, if you're considering like, well, can I use this machine for it? You want to ask yourself how strong the CPU is, how many threads it's got, and how good your RAM is. Not all machines, especially smaller, cheap ones like Raspberry Pis, are particularly good fits for fuzzing. On a fundamental level, though, fuzzing relies on probability. And there are some problems for which probability is not a good fit. If it's not a good fit for probability, fuzzing is probably going to be extremely difficult. Some of the subproblems in fuzzing are non-trivial. Some of them may even be NP complete. And the code coverage algorithms I walked you through often have a lot of limitations, miss a lot of spots, take the wrong things into account. It's hard to say much with certainty about path complexity in a binary. We make a lot of assumptions, and some of them are make it so that we can do stuff, but also limit our ability to be correct. Fuzzing itself is just never usually tells you why. You sometimes get results out of a fuzzer and you're like, why does this work? What does this do? Sometimes that can be more effort than understanding and running the fuzzer in the first place. And then you should always keep in mind that figuring out how to run your fuzzer, which is a practical stumbling block, is a non-trivial question. We don't have a good answer for it as a field. How do you know when it stops making progress? The going right now is 24 hours, but it actually might be much closer to 168. It might be even longer than a week. We don't all the way know. So a lot of times it's a gut check. So run through the parts of a fuzzer, some of the algorithms they use for their jobs, some of the limitations. This is just probably what's a good target and what's not. So parsers are a classic target. Parsers and fuzzing have a very close relationship. They are extremely amenable to both generational and mutational algorithms. There's a lot of input space to explore, and they tend to have a lot of problems that fuzzing is very good at finding. There are things that don't look like parsers, but you can think of as a parser. I once got into an argument with an academic who believes that every program is secretly a parser, and I did not win. So if your code loads or stores any data, you have some sort of parser there. You just might not know it. And those areas tend to be extremely fruitful for fuzzing. Command line utilities were the first target for fuzzing, and they're still an excellent one. They take strings of bits go in, bits come out. Bart Miller has a 30-year retrospective paper that's extremely good and targets many command line utilities, and classic fuzzing is still remarkably effective. Text-based APIs, cloud APIs often do extremely well as fuzzing targets. And then shared libraries generally also do rather well as fuzzing targets. Things that don't do so well, or maybe aren't a good fit, things with GUI-only access tend not to translate well to fuzzing algorithms. It's hard to translate that into meaningful random patterns that are actually different. However, if you got a file uploader, you can fuzz the stuff that goes up via the file uploader. Deep, complex, non-visible state, also rather difficult to fuzz because you're missing a lot of information. Complex sequences and exchanges, also problematic. And the reason is they're difficult for probability to help you. There are other things that are also difficult for probability, and classic stumbling blocks reflect that. So kernels have deep state, network protocols have complex sequences, and then magic numbers and tight branches rely on you finding that exact value and 2 to the 64 or worse. Probability is not your friend there. You're unlikely to find it, although symbolic execution does perform extremely well here. And for all these limitations, someone has tried to build a fuzzer or part of a fuzzer to get around it. And some of that research is very fascinating and very brilliant. But generally those are things, those are issues. So who's using fuzzing and why? When I first started talking to people about fuzzing as a researcher, I got some very strange responses. I'd get like, this fuzzer is great, it does all the right things. This fuzzer is terrible, it's awful, don't touch it. Why is everybody yelling? And why can't we agree on anything? And I eventually came to the conclusion, now this is my opinion and my sort of taxonomy of who's in fuzzing. So this is not conventionally agreed upon by any stretch, but this is the realization I had. There are different populations in fuzzing, and they've got different goals and different values, and they need different fuzzers. I don't think that there's one fuzzer that works for everybody or every group. If someone tells you that one fuzzer is the only fuzzer in town, please be very careful. I present this to you so that you can use your own critical thinking when evaluating someone's opinion or analysis of a fuzzer and seeing whether it works for you. So let's start with the group that everyone tends to think of when we think of as fuzzing. It's the offensive folks, the red teamers, vulnerability researchers, penetration testers, bug bounty hunters. They have some goals. They're interested in finding vulnerabilities. One or a chain is fine. Anything beyond that's really a bonus. You want to pwn a box, you really only need one way in. Anything else is, nice to have as a backup. They want to find it really fast. They want to find it before anyone else. They prefer other people have a difficult time finding it. And I don't really care about why something works. A very established penetration tester broke my heart when we were talking about races in a scheduler. And he's like, I don't care why it breaks. I just need it to break consistently so I can get in, get root access, and get on with my day. I'm like, but don't you care about why? It's so cool. He's like, no. So that was my realization that some people don't really care about why, and they don't care that the fuzzer does not tell them why. It's not part of their values. So if you're part of this group, you are interested in bugs that are exclusively vulnerabilities. You don't care about bugs that aren't exploitable. You want a really fast time to that first find. You want a fuzzer that'll find stuff that other people don't find because it will increase the value of your find and the duration until probability that your exploit will be useful as long as possible. And another feature that this group might be interested in is something that doesn't require source, something that works on a black box. Because if you are a third party or an external tester, you probably don't have access to the source all the time. So something that doesn't require that might be real interesting. So I mentioned a group might find libfuzzer interesting. This is them. Because libfuzzer exits as soon as it finds its first crash. It does not waste your CPU resources. And some of the independent researchers I've talked to usually have a couple targets going in sequence and sort of parallel. And so they don't want to spend CPU time on a target after they found an exploit. They want to move that CPU over to the next thing in the sequence. So libfuzzer exits as soon as it finds it. It doesn't waste CPU resources looking for anything else. For this group, that's actually very appealing. mopt AFL in the Magma paper found a bunch of bugs that other fuzzers didn't find. The catch was it had to run for 7 days to do that. But if you've got the CPU time and the power, that might be worth it to you to find stuff that other fuzzers don't find. Another group that's similar, also in the security party, is the blue team. These are often applications security engineers, they're security consultants, they're often charged with securing both a product and an enterprise. If they're fortunate, they only have to worry about one. And their goals are slightly different. They want to find all the vulnerabilities. It's not much good to say to your CISO that I patched a vulnerability and then we get owned next week by someone who found a different vulnerability. You kind of need to patch all the holes. And you don't necessarily care that much if other people find them, as long as you find them before release. If they aren't patched before then, that's less of a thing. This group cares a little bit about why, because they want to know if they've got a systemic security problem, like consistently unsecured IDs or tokens, or whether it's like a one spot. They're probably going to look for something that probes as much of the product or target as possible because they need to find all the vulnerabilities. They're not really as interested in regular bugs, but they do care about finding all the vulnerabilities. They probably want something that will complement security practices like security audits, other tools. They'll be looking for something in like basically a security analysis workflow. It's not super standalone for them. And then fuzzers that might appeal to this group, AFL Go could be a good fit as part of a code audit. You do the manual audit and you're like, that section over there, that section looks really dodgy. And you point AFL Go, which is a directed fuzzer, at it and see if you can get something out of that area. Instead of trying to fuzz the whole thing and things you think are low risk, you can focus it on high risk areas of the code base. Hong Fuzz and AFL are code coverage based, try to give you, again, a sense of covering more of the product. And they receive a lot of active development right now, so they might be good at finding new things. These are not like hard and fast recommendations, but I want you to think through the logic of what your goals are, what features you want to find in a fuzzer, and what fuzzers might have those. Next party is one that's sort of new, and these are sort of the software owners. You could be an engineering manager, a lead software engineer, QA engineer, a triage engineer. Sometimes as an engineering lead, an engineering manager, you spend a lot of time in triage. My personal record is 36 hours in a single week and 6.5 hours in triage in a single setting. So if you're part of this group, you care about finding all the vulnerabilities. You also care about finding all the non-exploitable bugs. A crash or hang, even if it's not exploitable, is still a problem that you need to fix. You generally want to find them before release so you can triage them, even if you decide not to fix them before release. And you really care about why. If you've ever seen a bug report, the more detail about why this is a problem, the faster I'm able to assess how much engineering effort is needed to fix it, which group should do it, and generally how to get that in the pipeline faster. Bug reports are like, it doesn't work. I'm like, well, we have to budget time to figure out triage and diagnose it. And that means that I don't know how big of a piece of work this is. And those tend to fall to the bottom. As a software owner, vulnerability reports are just one type of bug report, and I have to worry about all of them. So why can be very important to this group. So you might look for targeting specific commits, CI/CD integration. The fewer interruptions to your workflow, the better that goes. Testing stability. You want the fuzzer to perform sort of reliably. You're probably interested in more than just vulnerabilities. If it crashes your program, it's still bad. And then code coverage, again, might interest you because you want to sort of cover all of your code base. You're responsible for all of it. And for this group, I actually think classic fuzz testing has a lot to offer because it finds crashes, hangs, or inconsistent behavior, much of which may not be exploitable, but is still your problem as a software owner. Tofu is a fuzzer that was built explicitly for the CI/CD pipeline. That is what it's designed for. And then Microsoft OneFuzz is a new player on the scene. I haven't personally played with it, but it does market itself as for developers and for a development pipeline. Now, our last group is a little bit strange because its goals vary. I've met academic researchers who bleed blue, academic researchers that see only red, some that are focused solely on training the next generation of software engineers to write better, more secure code, and others that are starting more fundamental aspects of computer science. They're not really interested in security for security's sake. It's how they explore their area of research, and security happens to be the path that leads through that. If you're in this group, the thing you're generally looking for is a benchmark. You're looking for a good substrate to test your new ideas. You're looking for something publishable and something citable. Your super secret fuzzer that I can't talk about is very difficult to use, and my job is to talk about stuff or do research on stuff and then publish papers about it. And then fuzzers that are appealing to this group are generally AFL. AFL is the benchmark to end all benchmarks. I've only seen a few fuzzing papers that don't include it. It's given rise to at least 28 different fuzzers, such as AFL Go, AFL++. I stopped counting at 28, and easily a dozen have come out since I stopped counting a year ago. A lot of times what we do as academics, we eventually develop our own to test new optimizations and new features. So talking about AFL, let's talk about AFL. AFL is arguably the most famous fuzzer in the world. It is named after a breed of bunny. I cannot convince Google that I'm not interested in the Australian Football League, but if you are in security, AFL means the fuzzer. It is so famous, it needs shades when it goes out in public. It was developed as a side project by an engineer at Google and kind of took over the world, partially because it was open source. So characteristics is gray box. We are working with an instrumented binary. It usually uses mutation, although I'm aware that there's a grammar-based extension. Should you feel that it's necessary, you can use dictionaries to tune the mutator to only mutate certain sections, which sort of gets into generational, but that might be a bit of a detail. It defines interesting as an increase in code coverage or a crash or hang. You can exit it by setting a timer using Control-C if you're bored with it, or in theory, it can run out of seeds. I've never met anyone who has ever seen AFL run out of inputs to test, but it is theoretically possible. And then we have a thing called a driver, also known as a harness. This is a glue or translator program between the target and the fuzzer. Not all fuzzer and target combinations need them, but usually when you're working with AFL, you probably do. AFL largely only speaks standard in, and if your program does not speak standard in, you're gonna write some code in between. And that code is actually very important to getting efficiency out of AFL. AFL has a lot of parameters to tune. Please use them. AFL is very easy to get started with, and I think that accounts for a lot of its popularity. Is it's really easy to spin it up and get it started, but to really, really get good performance and efficiency and awesomeness out of it, you're going to need to spend a fair amount of time and effort on it. And like all good superstars, it has a posse of tools to help you with that. The ones I recommend for new people are AFL Min and AFL Plot, but it has a small zoo. So things I've seen people screw up with AFL. First of all, is understanding that AFL has a life cycle. We start with you and the target program and figuring out what fuzzer you want. In this case, I'm going to assume you decide it's AFL. You probably need to think a little about that. There are many, many more fuzzers in the world. You're going to do prep work. You're going to get your initial seeds, your initial inputs. You're going to write a harness here, lovingly drawn as a harness to help you carry the box. You're then going to tune some parameters. You're going to feed it to AFL on the server. It's going to run. You're going to need a bunch of stuff in the results directory. You're going to need to review that and try to understand it. And you're probably going to need to rerun some of it to test to see if it actually works. If you're lucky, you get the thing you wanted. If you're not, you might have to go back and start the process again. So everyone comfortable with sort of this life cycle diagram? Cool. So the thing I see people screw up at the start is they don't realize that they need to have the source to instrument. You can run AFL as a black box. It's not great. It's not very effective. Doesn't do well. AFL is not really worth running if you don't have the ability to instrument. The prep step also gets neglected. You should spend the time to develop a good initial corpus. Those are the initial inputs you feed the fuzzer. You should spend some time working on making sure your driver and or harnesses are good to go. One single function call in one driver is unlikely to really leverage the full power of AFL. And you should pay special attention to things like shared libraries. You really, really want to instrument the whole binary. Otherwise, it treats things it doesn't instrument as black boxes, and we're back to basically random fuzzing. It's not very effective. I see people ignoring parameters. You should tune them. They can be very effective. Be careful with the at parameter. It lets you chew on file names, but sometimes people chew on file names and not the actual body of the seed, and that can be a problem. And then when you're running it, AFL is very fussy about its processor settings. You usually need root or admin access to change those. If you don't have it, it can be hard to get AFL to do something useful for you. And then running the fuzzer long enough. One of the things I think surprises people is realizing how long you really need to run a fuzzer to be certain it's effective. I'll get students who are like, I've run it for 30 minutes and nothing happens, it's broken. I'm like, well, you know, going rate's 24 hours. Might even be a week. And their jaws hit the floor and they stare at me in sad disbelief. I'm like, well, you see, you're gonna have to wait a while. They're like, but the homework's due in 2 hours. I'm like, well, you should have started earlier. And sometimes you'll have to repeat the fuzzer. In research, we expect to repeat fuzzering runs at least 10 times to account for some of the stochastic nature and the variances. One single fuzzer run may not be representative of what the fuzzer can find because it's kind of a roll of the dice. You get lucky sometimes and sometimes you don't. And you'll need to understand that. So then reviewing and analyzing the results, a lot of people do not budget enough time for this. This can be longer than the fuzzer runs to fully review and understand your results. And one of the gotchas is that people see the crash counts. They're like, woohoo, I found a bunch of stuff. Well, a crash is not necessarily a vulnerability. Not all crashes are exploitable. And AFL is actually rather bad about counting and telling you what it's got. It's pretty sure when it's found something, but exactly how many things is sort of an open question. It does try to figure out if you got unique crashes, but my personal record is 52 unique crashes for 4 source bugs. There's a lot of duplicate crashes to go through and figure out that they're not real. I actually only had four problems. So that can be a great place where you spend a lot of effort without realizing it. Now, if you remember nothing else from this talk, if you don't remember what fuzzing is, but you remember this, I will be happy. This is a friend of mine who's a very accomplished vulnerability researcher. She prefers to remain nameless, so we're just going to quote her. But she is very insistent that the two most important things in fuzzing are a good harness program that probes your target and really good seeds. The next question people then ask me is like, well, all right, how do I get good seeds? You've convinced me I need good seeds. Well, in the general case, we really don't know what an optimal corpus looks like. So I can give you heuristics and things I've done, but I cannot say that like we know how good this advice is because we can't really evaluate it. In general, you want us to get to know the target, run it a few times, examine the source, examine the binary. Things I have personally done to get a good initial corpus, or an initial corpus, I should say, is I've rated the unit test directories of the project if they're available. I've run strings in a binary and edited it down to the strings I think are interesting. I've run the program a few times and found a few valid inputs. I'm like, all right, that's close enough to start. Or as a lot of people do, is you do some reverse engineering to really figure out what you want and where it looks interesting. As a friend previously quoted, says she spends more than half her time doing the reverse engineering than doing the fuzzing to make sure the fuzzer is pointed at the right stuff with the right seeds to find the things that she has identified as problematic in the reverse engineering. AFL has a thing called AFL min that will help you keep your corpus like lean and mean and in good fighting shape. If you come up with a couple seeds and you want to make sure there's no cruft, that's a good tool to run. And then before we get into the lab, I'm going to do something slightly out of order. I'd like to thank the ShaktiCon organizers because they've been busting their butts for months to put this on, and it's been a fabulous success. If you have some time, please say thank you because they have done a lot of work. I'd like to thank my long-suffering advisor, Dr. Wusong Feng, the National Science Foundation that funded the work that put together this lab you're about to do, the security lab here at Portland State, and my movie crew and guinea pigs who have patiently listened to me give many practice versions of this talk. Also have a couple of papers that might be interesting. If you read only one of these, read The Relevance of Classic Fuzz Testing, How We Solve This One. It's a good tour of 30 years of classic fuzzing, what fuzzing can still do. Fun time. All right, so here's the lab. It is public, it is available, it'll be on the internet around the clock. So if you do not feel like doing with it at 9 in the morning, and I never want to touch code at 9 in the morning, so I'm very, very sympathetic. The link will be up, it's public. It does use Docker and it does use GCP. I have done it locally, but I have never done it on Windows. So if you're on Windows, I'm not sure I can help you, but I can try. You can find me via email or you can find me on Discord. I'm generally more active on Discord on the weekends or at night in Portland time, which is morning for you guys. So during the day, I'm often not available because I've got to do other stuff. So thank you for listening. And if you have questions, I'll take them now. If you want to get started on the lab, that's cool too.
Yeah, there are some questions which I can ask you right now. And the labs are to be done offline, right?
They can start them now.
Okay. Yeah.
I did them a few weeks ago, so they should all still be good and the direction should all still be up to date.
Okay. Mm-hmm.
But if they want to put them off, that's cool. If they want to start them now, if they want to go have a drink of tea, I'm not going to argue.
Yeah, all right. Yeah. So the first question is, did you draw your own pictures? Really
yes,
good.
and it took an excruciatingly long amount of time. I went through 6 drawing programs. I've officially learned how to use an Apple Pencil for the first time. Yes, I drew those diagrams. Anything that doesn't have a credit or a source, I drew or took a picture of.
Okay. The next question, what essential computer science skills do you recommend someone has as a basic foundation before they get into fuzzing? Programming languages or knowledge of assembly or something?
Well, a little bit of all three. Algorithms is a good thing. There is a lot of heavy PL theory in some of the bleeding edge fuzzers. There is a lot of type theory in there as well. I'm more on the systems practical end. So I am evaluating fuzzer performance as opposed to building my own fuzzer right now. but there is actually a fair amount of theory that shows up. The reverse engineering aspect is certainly a thing that is used by people who are using fuzzing in practice. So I think there's a little bit of a split, whether you're so interested in building the next greatest fuzzer or using the existing fuzzers effectively. I think a lot of founding in reverse engineering and binary analysis is extremely helpful if you're trying to use these in a practical sense. If you are interested in building the next one, then more foundational things like algorithms, PL, type theory are much more relevant. I go to a fuzzing reading group, and whenever they hit like a new fuzzing paper with a novel methodology, I spend half the paper asking people what it does because my theory background is rather rusty. Somewhere there's a cave painting that depicts my graduation from CMU. It was a very long time ago. Thus, a lot of that stuff is things I've long forgotten.
Okay, the next question. When studying fuzzing, are there benchmark programs that people fuzz against to check performances?
Yes, so in 2018, a paper comes out called Evaluating Fuzz Testing. It's extremely controversial. It rifles through a lot of fuzzing evaluations and finds problems in just about all of them. One of the problems highlighted is we cannot agree on exactly what to test. So it's hard to compare fuzzer A in paper A to fuzzer B in paper B if they're tested on entirely different things. To that end, a few things have risen. There is FuzzBench, which is aimed at protocol fuzzers. There is Magma, which is a thing I've referenced a few times here, and I have links in the slide. I'll eventually put those on GitHub, probably tomorrow morning. And that one focuses more on classic things. There's also Unifuzz, which I don't think is actually a great approach to a benchmark because it does not have ground truth, but it does exist. So we've been trying as a sort of research area to standardize on what programs make good benchmarks and good tests. And we have not yet converged on an answer, but I think Magma's answer is the best one. It's also open source and on GitHub, so you can pull that down and play with it tonight if you wanted to.
The next question, what's up with the rabbits? Sounds like a fun story.
I do not know why the creator of AFL chose to name after rabbits, but ever since then, rabbits are very associated with fuzzing and fuzzing iconography. And we did have Easter here in America, so my mother sent me a basket with that cute little fuzzy chick that is depicted in the "you must be this tall to find this bug." I didn't really know what else to do with it, so I was like, oh, you know what, I'm giving a talk on fuzzing. It's fuzzy. I'll put it in the slide deck. Yeah, a lot of fuzzers have puns on things that are fuzzy. I don't know, it's a cultural thing that's just sort of stuck around fuzzing as a community. Rabbits are very fuzzy. I guess they're popular for that reason.
Yeah, all right. The next question, is there parallel distributed processing for fuzzing? This is common for machine learning to speed up things. Curious if
some
it's
of them,
happening.
Some of them have it, but it depends on the fuzzer. So some of them do have distributed or parallelizable parts or go after something that's highly parallelizable. Not all of them do. So that would follow under the secret sauce question. Some fuzzers are deliberately built to have high parallelization or distributed computation powers, and that's what makes them special. But not all of them do. They certainly exist.
Mm-hmm. Okay. Another question, what is the practical use of fuzzing with coding?
Well, how do you feel about finding bugs? If you write code, you probably want to find your bugs. Fuzzing can help you do that. And it can often find things that your QA folks or the people who are writing code don't think about. Like one of the things is fuzzing is that it will find stuff that you were like, I didn't know it could do that, and I wrote it. Thanks, source of randomness, for finding that. It's not a super fun feeling as a developer to discover that Dev Rand knows more about the thing you wrote than you do, but it's better for you to find it than somebody outside the organization who might do naughty things with it.
Okay, that's all what I could see in the chat. If there are more questions, please do post them in the chat because we have 10 more minutes for discussion. I actually had a question. So if you mentioned about fuzzers which could be used by developers, are these fuzzers language dependent? So yeah, I don't remember the names of the fuzzers you mentioned, but yeah, the question is.
So AFL Go is the open source directed fuzzer. And that one is built on AFL, so it has some of the limitations that AFL does. It speaks only standard in. It was largely aimed at C binaries, so it doesn't really work on anything like JavaScript.
Yeah,
Tofu also, I think, was C targeted. And I have not looked into Microsoft OneFuzz, so I don't actually know what its language restrictions are. But usually it's aimed at compiled code. So we can fuzz Rust in some cases as easily as C, provided it's been compiled down. WASM compiled to a C target also works in AFL just fine. I've done that. But yeah, so where it targets is one of its chief limitations. Some fuzzers really can only fuzz certain languages or styles. Navex was developed to go after JS. Montage, I believe, also goes after JS. So you would be looking for a fuzzer that can handle your language as part of that. I don't think there's a fuzzer for every language and style yet. I think there's still plenty of room for innovation and development and specialization.
Yeah, and which is the fuzzer that you would suggest for network protocols if you have like a PCAP or
Bufuzz, but Bufuzz I think is white box.
Okay.
AFL Net was one of the early fuzzers to look at network protocols. Fuzowski, I believe, is another one that's a network protocol fuzzer.
Can you name that again? What was it?
It's called Fuzowski.
Okay.
Bufuzz. And then AFL Net. AFL Net is based on, you guessed it, AFL. AFL has a lot of grandchildren.
Yeah, and one more question. How so when we have crashes, how can we detect what are the false positives and repetitions in there? Is it just manually going through everything, or the fuzzer also provides some way to?
Almost all of them, it's up to you to figure out how to do that. I know some people who automate it with that scripts they wrote to take everything out the crash directory, feed it to the target program and see if it actually crashed, and if it didn't, discard it. And then figuring out whether they've all got the same root cause was a thing that I think everyone's largely done manually. I know there's been some preliminary research there, but ultimately it's things you do manually. One of the things I like about Magma as a framework is it tells you when you've hit specific CVEs. So you don't have to do that resolution for you. It knows that you triggered that crash and found that specific bug. So it says you found these 10 bugs out of the 20 possible that we know about. And I think for evaluating a fuzzer, that's extremely useful, but that's less useful in practice on a target where you don't know what the ground truth is. So it's useful for me as an academic, but it's less useful for you, someone who is trying to find unknown vulnerabilities.
Yeah.
And I think for the people who are looking for the unknown stuff, there's a fair amount of either automated scripting or manual testing that goes into that.
All right. I don't see any other questions. I will just post the link for.
Yeah, and I'll drop a bunch of links in the Discord. Just tell me which channel to do it in.
I'm thinking, yeah, you should have access to the discussions and you could post it there. Yeah. Yeah, all right, then I guess that's it for today. Thank you so much, Allison, for that wonderful talk about fuzzing and how to get started with it. I always, yeah, I tried my hand a little bit with AFL someday long back, but maybe I'm going to start again doing something with it. And I'm sure that, yeah, many of the attendees are also already on the labs and trying to play with it. So thank you so much for your time.
You're welcome. Thank you all for listening. I hope it's useful and enjoy the rest of ShaktiCon. There's some really cool speakers coming up today.
Yes, I think our next talk will start at 9:30. So we have in 8 minutes. So.
Right, a half hour off. Okay, then I guess I will stop sharing and start posting stuff.
Yes, yeah, thank you so much, Allison.